Alright guys, welcome to this second stream. So in this stream we are going to continue with building RAM 64. RAM 64 is basically a combination of in total 8 RAM 8. So in the last stream we already built the RAM 8 chip. Let's try to draw the diagram of a RAM 64 chip. Okay. So one thing is clear, we want a RAM 8 chip, right? We want a RAM 8 chip, and in total we need 8 of this. This canvas size is going to be much smaller, I think. Let's open up a new canvas, a much bigger one. Alright, this size will suffice. So we have RAM 8. We have 8 of this stacked together. For RAM 64 we are given a 16-bit array as input and a 1-bit load variable and 6 bits of address variable and 16 bits of output variable. Let's check the implementation of RAM8 as well for the reference. So RAM8 contains, let's open up our implementation of RAM8. Okay, this is our own implementation of RAM8. So for RAM8 we used 8 registers and demux 8-way and mux 8-way of 16 bits. Now we have to use 8 of this RAM inside our RAM 64. So what we are given? We are given an input of size 16 bit. This is input. This input, if we directly give it to all of these RAM chips like this, and different RAM chips correspondingly, and for all of these individual RAM chips we also have input. So yes, we have already given the input. There's also a load input and address input for each of this RAM. So we have to figure out what to give to this load input and this address input. Let's see. So for RAM 64 we will have 6-bit address. 6-bit address. It starts from 0000 6 times and 1111 6 times. So 000, all zeros will select the first RAM, and all ones should logically select the last RAM, and we have to implement that functionality somehow. So what we want is basically according to this address bits we should toggle this load bit. Suppose if it is all zeros, then we should provide whatever load input we are given in this RAM 64 to the corresponding RAM 8 chip. And inside that RAM also we have to provide another load. Okay, this load and this load will be similar, will be the same, but this address should be either first 3 bits or last 3 bits, I guess. So let's try to walk through a simple example. Suppose we are given all zeros inside the address bit. Address bit is all zeros, and load bit is provided as 1, and inside input we have a random input. Let's say 101010 16 times. Let's give a decimal input instead of binary. Okay, so in this case, this input should go inside this first RAM 8, and inside that RAM 8, this input will be this, it will be the same, and the load bit, okay, so the load bit of this first RAM should be 1, and accordingly this bit will also be 1. Now we just have to figure out how to map this address bits, this and this address bits. So suppose if are given 0000, so in that case we are selecting first RAM, but inside this RAM we have to select either of this register. How to select any one of this register? Any of this register can store a 16-bit value, so it depends on what we give inside this address bit. So let's say if we map the first 3 bits for all of this, for selecting any one of this RAM from 8 RAMs that we will be having, and the last 3 bits will select any one of this register. Any one of these registers will be selected by this last 3 bits. So let me try to draw what I'm trying to say. So this RAM, this load is this one, and this address bit is of 3 bit, which is this one. Now if we are also given another load for our RAM 64, so this is a load for our RAM 64, and this load will directly go into all of this. No wait, the load shouldn't go like that. The load should go inside any one of this RAM based on the first 3 bits. So we used a demux 8-way for that kind of logic. So suppose if we use the same logic over here, we provide the load to a demux, it's a demux, and we have 8 of these outputs, and these outputs go directly to all of these RAMs. And this demux should contain a selector bit, and it is of Demux 8 way, so 8 ways, so we have to get 3 bits of address. So we provide, let's try to draw the individual bits. If we provide this address, let's call it A. So first bit A0, second bit A1, third bit A2 will be provided to this mux to select any one of this RAM. Now that is clear, but we also have now this address bit, which is of 3 bits. So if we directly provide the remaining remaining 3 address bit, which are A3, A4 and A5 directly to this RAM, then in theory it should select the correct register. Zero 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 000 000. It will select the first register inside first RAM to store this 16 bits of value. And if it is 000 and 001, then it will select the second register inside the first RAM. Okay, the logic seems clear, I guess. And we also want this output. So for the output, we can directly use this kind of logic where we use a mux 8-way and 16-bit. All of these RAMs will also this the output inside this RAMs take care of itself. Alright, the output will be selected based on this address we are given. So yeah, it will be selected by itself. So you can directly map this outputs to a mux. It's an 8-way mux, so there are 8 total inputs and 1 output. This output is this variable, and we will select this mux based on address. Okay, so we can use these 3 bits over here as well, I guess. For the selector. Okay, so this seems clear. Let's try to implement it in the code. So we need 8-way mux, so let's copy this from whole. We have a 8-way mux. The input bit is load, which is correct. The selector bit, now the selector bit can't be directly addressed. We only have to give the first 3 bits. So for that we can do something like this. We can individually select the selector bits. So for the first selector bit, we will provide address bit 0. Similarly, for the second selector bit, we will provide for the third one. Now we have this thing over here, and we have all of this individual outputs. This output should go inside this RAM 8, so we can use this logic, directly copy this thing over here and replace all the registers with RAM. Want to replace register with RAM 8. Okay, we have this part implemented as well. Now we also have to give this input bits, because our RAM has input, load and address as well. We have already provided input, load, but we are yet to provide the address bit. This RAMs will have same address bit. Right. Let me check how to edit multiple lines at the same time in Vim. To edit multiple lines at the same time in Vim. Use macro code with QA sketch. This command basically inserts a comma at the beginning. Yes, I know this trick. Control V. Shift I. Space address equal to, we can't directly use the address bit, we have to use something like this, address bit 0, and address bit 0 will be selector bit third. Okay, now we can edit this thing. That we also want 0, 1 and 2. Address bit 0 is equal to selector bit 3. Address bit 1 equal to selector bit 4. Okay. We have to use address over here, not selector. Address. Wait, if we use address, the same name for both of these variables, isn't it going to conflict? Let's try to implement it. If it gives error, we will do something. 0, 1, 2, and this should be 3. And address bit 1 should be address 4. Address bit 2 should be address bit 3, 4 and 5. That is it for the first RAM. Let's go. Let's try to check it if it is correct. Address bit 0, 3, 1, 4, 2, 5. Okay, it is correct. Let's repeat it for all these RAMs. Now we have to replace. Do we have to replace any of these numbers? Well, the address bit 0, 1 and 2 for the RAM will remain same, and the input address bits will also remain same. So I guess we don't have to edit anything else. Okay, alright, so we have taken care of this address bit as well, this load bit as well, this inputs as well. Now what is remaining? Okay, now this part is remaining. Let's get this mux. this RO0 comes out from RAM 8, so this inputs are also mapped correctly. You only have to change this selector bit. So for selector bit 0, we have to provide 0th address bit. This should be the last address bit. 2. This should be 2 as well. This will be 1. This will be 1 as well. Okay, so we have implemented the code according to this diagram. Now let's try to load this code inside our simulator. We have implemented a RAM 64. Thankfully it is not giving us any errors, but now let's try to load the RAM 64 test script as well. Great, so it is loading the values correctly as well. So from this few inputs, it seems that our implementation is correct. So while it is loading, let's also try to see how we can implement other chips. The next chip is a RAM 512, so we can use the same logic that we have used inside the RAM 64. RAM 512 is basically 8 of this RAM 64, right? 18 to 64 is 512. Oh, yes, it is 8 of this RAM 64. So for RAM 512, we only have to change RAM 8 to RAM 64. But wait, we also have to provide 6 bits of input. It seems our logic is correct, but it is going to get much more complicated as we move closer and closer to RAM 16K. Because for RAM 512 we have to provide six address bits for all of this. How are we going to do that? Plus RAM 512 will have it will have, let's check the HDL file of RAM 512 now. RAM 512 HDL. So yeah, it will have 9 bits of address bit. So we have to edit this mux address selector bits and this address bits as well. also these address bits. Is there an easier way, because this is going to get much more complicated? Let me save this diagram. RAM 64. So for RAM 512, basically we will have a RAM 512 over here. We will be having 8 of this RAM 564, not 512, 500 RAM 64 stacked. We will have 8 of this, and this input address bit will be of 6 bits, and the selected bit will have 6 bits. It will have RAM 512 contains 9 bits of address. So if we provide 6 address bits over here, then we are only left with 3 bits of. So this will remain same. We will only have 3 bits for the selected bits. So, and similarly over here as well. So we only have to edit this address bits only. So I guess it won't be that much complicated as I thought. So let's try to load the HDL file of RAM 512 now. RAM 512 HDL. And we can directly copy all of this code. Yank one Click the first file, yanking the text you want, then open your second file from within here and paste it. Open both files together in a split window. We already have it open in a split window. Navigate between them using Ctrl W, up down, either by this. Right, this seems simple. So we have already yanked the code. Now what we have to do is paste. It is inside A RAM 512. RAM 5, RAM 64. No right since last. Why can't we paste it? No right since last change. Add. Oh, wait, what did we do? Oh, wait, it pasted everything from. It's alright. We can delete it from this part, I guess. We want up to here. Right, we have it copied now. And so our test script has ended also. It was successful. That means our implementation of RAM 64 was correct. Let's continue with the RAM 512. Now in RAM 512, we just have to change this address bits. Plus we have to replace RAM 8 with a RAM 64. We have to replace RAM 8 with RAM 64. Now we have to add 3 more of address bits. Address bit 0, 1, 2 and 3. This will be 3, 4, 5 and 6. Address bit 4 will be 0, 1, 0, 1, 2, 3, 4. This will contain the 7th address bit. Address bit 5th will have 7 and 8th address bit. Okay, so that's done, I guess. We have all the necessary address bits, right? Let's try to load this script now. This inside B RAM 512. Oh great, now for RAM 512 we get this kind of GUI. Oh, where did the GUI go? Okay, so here. Great, so the script is also working as it should be. Now let's check which one is next. We have completed RAM 512. Now we have to implement RAM 4K RAM. 4K RAM will contain 8 of 512 RAM, right? 512 into 8 is 4K, right? Let's open up the HDL file of RAM 4K. Now we want all this copied. Similarly, for this RAM 4K, we have to edit RAM 64 to RAM 512, and we have to add how many of these address bits we have 12 address bits. So if we have 12 address bits, then if we use up 3 address bits for the selector, we will have 9 of this over here. RAM 64 should be RAM 512. Address bit 6th. We will have 9th bit. Address bit 7th. We will have 10th bit. Address bit 11. We will have, wait, this should be oops. Bit 6th. 4, 5, 6. We'll have the 9th bit. And address bit 7th. We'll have the 10th bit. Address bit 8th. We'll have 11th bit. Address bit 9th. We'll have the last bit. Address bit 12. That's it, I guess. 5, 8. 6, 9, 7, 10, 8, 11, 9, 12. Right. Okay, this script has ended as well. Let's load RAM 4K. Wait, why is it giving us errors? The specified subbus is not in the bus range. Which subbus is not in the bus range? Did we type something incorrectly? We know that RAM 512 contains 9 address bits. So we have given 0 up to 9 address bits. We have given it from 3 to 4, 5, 6, 7, 8, 9, 10, 11, and 12. This seems correct. Why is it giving us errors? It is only giving us errors for address bit 9. Wait, we only have 12 bits of address, so we can't use 12 over here. Wait, then where did we commit a mistake? Suppose we are having A0, A1 and A2 as the selector bits. That leaves us A0, A1, A2, A3 up to A11 for this address bits. A3 up to A11. So A3 up to A11, that's only 8 bits, but we have to provide 9 bits. It should work. 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, wait, yes, yeah, got it. Get in not found. Do we have to escape these characters? Okay, it is cleared. Now let's try to load it. Great, now it is not giving us any errors. Let's load the test script as well and let it run. Now let's do the same thing for RAM 16, which will be our last RAM. RAM 16K HDL. RAM 512 should be replaced with RAM 4K. Plus 9 will contain 12. Address 10 will contain this 13. Address 11 will contain 14th bit. Address bit 12th will contain address bit 15. Oh, hi Crazy Vortex. We are trying to create a computer from scratch, and we are using this hardware simulator to simulate all the basic chips. Basically, I'm going through this course, build a modern computer from first principles. Address bit 13 will be off. It will contain 16th bit. This is it, I guess. Inside RAM 16 we have 14 address bits. We are providing 14 address bits. Wait, did I overdo something? RAM 4K contains RAM 4K contains 12 address bits. So RAM 16K contains 14 address bits. To get 16K, we only have to use two 4K, right? We don't have to use 8 of this 4K. We can use only 2 RAM 4K. We have 2 RAM 4K, and to select any one of this, but in that case we have to use a two-way demux. So if we use a two-way demux, we can use a one selector. Demux two-way, four-way. Don't have a two-way demux. Wait, a simple demux is a two-way demux. Yeah, a simple demux is a two-way demux anyway. So we can directly use a simple demux over here and have 2 of RAM 4K inside this chip and provide 2 inputs to it, and the selector bit will be of 1 bit. So we can use the first bit for the selector bit, and all the remaining bits, if we have to use only 1 bit, that leaves us 13 bits, and we can provide those 13. Right, so in RAM 16 we are given 14 bit of address. If we only need 1 bit to select a RAM 4K, what are we going to do with the remaining 13? Because a RAM 4K only needs 12 of these bits, so 1 bit will be wasted. Now, what are we going to do with that remaining bit? And should we provide 12 of those starting from that bit, which will be first A1, or should we provide it from A2 up to end? That 4K means 500 into 8, which is 4096. So 16K will contain 4096 into, oh, right. We have 4096 into 4. So we have to use 4 of this. We have to use 4 of RAM 4K chips. So now it is solved. Now we can use the first 2 bits for this demux. We can use the 4-way demux for that. So it will be something like this. This will be 4-way. Wait, why did the mapping stop? Okay, now we have a demux 4-way, and first address bit will go inside 0 selected bit 0, and 0th address bit will go inside selected bit 0, and first will go inside selected bit 1. And we don't need this last selected bit. Now we only need 4 of this RAM key. So, and we have 8, I guess. 1 2 3 4 5 6 7 8. And let's delete the remaining 4. Okay, now we have 4 RAM 4Ks. And this RAM 4K has 12 address bits. Oh great, we have to edit this address bits as well. We have to shift the address bits. Now this address bit will start from 2 up to 14 up to 13, I guess. This will be address bit 2. This will be 3, 4, 5, 6, 7, 7, 8, this will be 9, and 10, 11, 12, 14. That's it, I guess. We can get rid of this address bits. Okay, so we have the address bits which starts from 0 and ends at 11, and the input address bits start from 2 and ends at 30, 12, 40. Okay, it's perfect. Let's copy it. 1, 2, 3. Now we also have to change R0 to R1. This will be R1. This will be R1 as well. Wait, it will also replace. Let me. Let's write it directly. This should be R2. And this should be R2 as well. This is RO2. This should be RO3. This will be R3. And we have to change the mux as well. We need a 4-way mux. Four-way 16-bit mux. If it is 4-way, we only need A, B, C, D. We can get rid of E, F, G, and H. And it will have only 2 selector bits. We can get rid of last selector bit. Great. So 16K is ready as well. Let's try to load it. What is it saying? E is not a pin in DMux 4-way. Oh yeah. Change outputs as well. A, B, C, D. DMux 4-way, so it has only A, B, C, D, not E, F, G, H. So we are done with all the RAM chips, only the program counter is remaining. Program counter will probably contain a lot of logic because we have to take care of different inputs like load, increment, and reset. So we'll probably do it in the next stream. So far it has not given us any error, so I guess our implementation of 16K is correct as well. And I guess this is it for this stream. We will implement program counter in the next stream because it will contain much more logic. So let's end it over here, and I will see you in the next stream. Bye.